Hello. Hi, Unexpected Maker. Hi, Beata. I'm trying a new mic setup today. Hopefully it's good. I saw Yanni was waiting with the deep diver gif. Get my windows all squared away here. You can hear me though, right? It looks okay on my end. It's just going to be mono. Loud and clear. Awesome. I was listening to it. It was a little bit fuzzy earlier, but we'll see. The nice thing about this is I don't have to worry about moving around. And I am trying the ultra low latency on YouTube as well, so we'll see how that goes too. I forgot to move my... I can always go to the old audio. You can hear me on the other mic now, I assume. Something happened on the USB, I think. Bummer. It looks okay. So yeah, so this is the other audio. I don't know what happened. Failed to read out thermal zone. I don't see any. This is all like boot stuff. Oh, that's garbage. I wonder what happened. I mean, I know Linux hates USB, that's for sure. But I was hoping this would be a good solution. OBS doesn't see it now. I got a Scarlett 2i2. It looks like it's okay. Hang in there, folks. I know you all are great. I'm unplugging it and plugging it back in. Oh, DCD's reading the USB book. That's awesome. What makes this harder is there is a cat on my lap right now, too. Oh, come on. Where's the plug? All right. I'm surprised Vin's on my lap even though I'm talking. I replugged it in. Yeah, I'll be better. Sorry. I don't know. Okay, I'm moving back to the old system. That's unfortunate. It just like disappeared from... It disappeared from OBS. Like I had it in there and then it wasn't. Okay. Sorry, folks. Hang in there. Well, I'm just going to get my headphones back on as a way to make sure that I'm somewhat close to the mic. And where's the other... What did I do with the other plug? I had too many cables on my desk. Let me tell you that. Oh, maybe it got... There it is. Vin, pick it up. All right, kitty, get up. I know. Sorry, folks. We'll get going here in just a second. She had to file her complaint that she was getting kicked off. I knew today would be like that. Trying out a new audio thing is always sketchy. I guess I could have tried it like under the hood. Okay, we're going. We're using... Let me know if that original audio was much better, although I think I recycled all the packaging already. I shouldn't have done that. But yeah, we'll go with this today. It should be fine. So let me say hi to folks. Yeah, M. Lindholm, thanks for saying the audio was back and gone. Hey, Dave. Hey, Bruce. Hi, Pierre. Hi, Unexpected Maker, Keithy EE, Ask Patrick W, Bruce S. Hi, Charles. Hey, Doctor. Hi, Hoo-Ha 007. Thank you all for hanging in there. Hi, Hams Labs. Hi, Skur. They were going good until this is loud. I can turn it down. Happy Friday, Linux 203. This should be kind of what it normally is. Hi, Xmicron. Okay, let's get going. Let me hide the... not this. Oh, we might do KiCad. I don't think so, though. Hide this. And we'll do housekeeping first. Hello, everyone. My name is Scott. This is a deep dive with Scott. That's me. I work for Adafruit. They're an open source hardware and software company based out in New York City. I work for them on CircuitPython. CircuitPython is a version of Python designed for microcontrollers. So really small, inexpensive, easy to access, easy to put in lots of different things, sorts of computers. And we try to bring the Python language to that. So it's really the merging of software and hardware in that world. So that's what CircuitPython is. That's what Adafruit is. This is a deep dive. They happen normally Fridays at 2 p.m. Pacific. We're a little bit late here today because I was trying to use a new audio setup that promptly stopped working right after I started using it. So that's great. Really good. But we're back with the old system. It should be just fine. Should be solid because it's what we've used for a while. Yeah, so this is a deep dive. If you have questions, I'm happy to answer them. I'm kind of in the middle of something, so we'll dive pretty much right in. Yeah, so they typically run for about 2 hours, so we'll be here for 2 hours. So that's plenty of time for questions if you have them. And next week will be on Friday as well, and then the next week after that, I'm planning on taking off. So the 1st of October, there will not be a stream. So 1 week from now, there will be, and then 2 weeks from now, I'm out of town, so there will not be. And is that all the housekeeping? I guess the cat down here, that's Spook. He's usually in here. The other cat that was on my lap is Vin. She usually doesn't like it when I start talking. So she peaced out. So Spook is epileptic. Occasionally he has seizures, but he's been really doing really well. So that probably won't happen, but I just like to give folks a little bit of a heads up for that. Yeah, could I set it up to automatically do like 2 hours of Spook just sleeping in the window? Yeah, it's getting rainier here too. That's what Bruce is saying. Hey, what's up? Bed intruder. Okay, so let's I haven't seen any yeah, open source lo-fi kitty cam, great filler. Yeah. I won't be here to run it, so we'd have to teach Vin how to run it, and Spook could just sleep there. All right, so let's us dive right in, I guess. I haven't seen any questions come up, so if you have questions. Otherwise, what I've been working on, I talked about it a little bit on Show and Tell, but I've been trying to get TinyUSB running on the Raspberry Pi. The Raspberry Pi, not the Pico, but the proper Raspberry Pi. This is something I've talked about the last few weeks, but because Unexpected Maker picked up the S3 work, and I looked at the datasheet and was like, like the only thing that really needs a lot of work on the S3 is BLE, and I need a break from BLE. So something that's been on my mind a lot is bringing TinyUSB and CircuitPython to the Raspberry Pi 4 in particular. And so I've been working on that and haven't been making a lot of progress, but it's like learning all about it. Yeah, and so I'll show you what my setup is. So unfortunately, the only power supply I had for the CM4 IO board is actually the one that I use for the overhead. I ordered more from DigiKey, but it doesn't come until next week. So I'll use CatCam here. Hi, Wendy. Yeah, we'll go to CatCam here. You can see there's CatCam, there's Spook. So let me show you the setup here. I won't be able to show it kind of like all the time, but I'll give you an overview of what I'll be working with as we work through stuff. So there's the cat, and I'm going to use CatCam to fly over here and show you my desk. So the setup that I have here is I've got this Salie, and I was running these wires into the IO headers of the so this is a Raspberry Pi 4 CM IO board. And sorry, this CatCam is not the best cam. The overhead's better, but we'll use that next week. So here you can see there's this CM4 module that's set down onto this board that breaks a lot of stuff out. So CM4 is compute module. So this is like a Raspberry Pi 4, but in like put it on a different board sort of form factor. I had the focus reasonable. There we go. And so the regular Raspberry Pi header is over here. And what I've got going out is these three wires are UART to a UART to USB converter. So that's how we'll monitor your UART output. And then this bundle of wires here is to a jlink there. And this is the new audio Focusrite thing that wasn't working. I've got power on a switch, so I can turn the CM4 board off and on. And I've got this, it's an SD card reader. So if I need to flash a new SD card, that's what I'll be using. So that's the setup that I've got. I haven't actually gotten to the point where I'm testing USB. So when I test USB, we'll be plugging it in there, but I'm not there yet, unfortunately. So can you get a GPU to run with that PCIe header? There's look up Jeff Geerling. He's a YouTuber that does a lot of Raspberry Pi stuff, and he's tested multiple GPUs on this header. So yeah, I think some of them can, but that's not what I'm focused on. So yeah, check out Jeff Geerling. He does a lot of stuff in that vein, testing and things. Wow, look at that white balance change. Okay, so there's the overview of my desk as it is right now. And you'll notice there's no keyboard because I have the keyboards out here on these mounts. So yeah, that's what I'll be messing with, and we'll go back to SpookCam now. And I'll stop making you. Ask Patrick W asks, what Macropad shortcuts do you have on that? I basically only have one, which is play and mute. Play and mute the my audio that I'm listening to, like the music I'm playing. So, yep. So we're back at CatCam, and let's go to the desktop here. And I'll pull this up first. So yeah, I just wanted to give an overview of, you can see I have the notes in the background. So a lot of what I've been doing is trying to figure out just like the development workflow. So they're more complicated. They're a lot more complicated. So a Raspberry Pi proper, these are what are considered Cortex-A class microprocessors. So they're microprocessors, I think, largely because the RAM is actually a separate chip. And it's 4 cores for the Raspberry Pi 4. And those cores are like fully capable of running Linux or anything. So what I got here is this is the USB to serial, the UART to USB output. This is my debugger. And let me pull up the code. So I've been cribbing off a number of sources that I will have to pull out into this other browser. What about peripherals? So I think the peripherals are pretty much the same. Let me see. Sorry, I just got a text message. That's why my brain stopped. So there's these files that you can get that are they're not full data sheets. They don't like to disclose, particularly the stuff about the GPU side of the Raspberry Pi, which is actually the main bit. The main thing in the chip, the BCM 2711 or 2835, like the main thing is actually the GPU. It's not the ARM cores. The ARM cores are just kind of like off on the side. So this is, you can find data sheets for the peripheral trees, but you can't kind of like find the thing overall. But this will tell you like physical addresses and stuff like that. And this is not for the right thing, but I thought I had it open, so I thought I'd pull it up. Yeah, so this is not for the one that we need, but you could basically treat it like the peripheral side of things is pretty similar. It's pretty similar to like a microcontroller. It's just a memory bus with registers for different things. The CPUs are actually the part that's a lot more difficult. So Doctor asks, so what's the big advantage you expect to have using a Pi with CircuitPython on bare metal? And the answer is HDMI. Like, hands down, that's the reason I'm doing this, is because the way that it starts up is the GPU actually starts and gets everything going, and then it loads stuff for the ARM cores and then runs the ARM cores. So the way that it works, and I have a ton of tabs open that are on this other Firefox window that I should drag over here. Because I'm sure that we will reference them. Maybe. Yeah. So we want that. And we want this. And we want this. And this. Some of these tabs I haven't had open for a while. CM4 datasheet. I have a lot of tabs. Yeah, okay, here. I think this is it. So there's two places I've been really referencing. So I should give a shout out first to CrowdSupply, the Piunora, which is probably not on the, oh, here it is. So this is one of the reasons I'm interested in it, and this is an idea that I came up with kind of in collaboration with Timon. So this is it's a Metro shaped, Arduino shaped, is the ARPi 4 essentially a GPU with a few ARM cores attached to it? Yes, I believe so. Yep. Isn't that a bit against the whole open source spirit of the project? The fact that the GPU is closed? I mean, none of the stuff that we're doing either, like, I don't have access to closed source stuff, nor will any of the code that we write be closed source. The GPU, yeah, is closed source, but it's documented enough to be able to spit stuff out. So, yeah, so Timon did this Piunora, which is really cool, and he sent me an early one that I've stashed away. But the idea being that you can treat this like Cortex A level thing kind of like a regular like microcontroller, and you get this weird world of like a lot of power, and some things like HDMI and PCIe, but you could treat it like it's a CircuitPython thing. So I love like mashing those two things together, and this is why I'm really interested in it. So check this out if you haven't already. Piunora is pretty awesome. And then Timon was starting to work on CircuitPython, and one thing he linked me to was this, I sometimes, Raspberry Pi 4 OS Dev kind of tutorial. And this is a really great reference for very simple bare metal things. So you can see it's like 12 parts. It's sorted a little weird because of the last three. Hi, Johnny. But this has kind of got me going. And you can see here that part 5 is frame buffer. And so it's like part 5 where they start to like poke things to the GPU to show things on the display, which is awesome, right? So like, bit confused by the Pi Foundation using a relatively closed thing for the Pis. That's all. I think the reason that is because like the folks that started the Pi Foundation used to work at Broadcom, right? So like they had all the background on those chips to begin with, and I think they worked on those chips, so they had access to the closed bits. And this is why like BeagleBone Black is meant to be an alternative that's more open, right? You can use that if you like. But the fact that the GPU actually starts up these chips is actually quite beneficial because it simplifies a lot of the work that we would have to do. Like we could potentially do like other Cortex A level stuff once we kind of get it going for CircuitPython and TinyUSB, but the startup stuff is different. So like Raspberry Pis are actually a bit simpler from my understanding because the GPU does a lot of that work for you. Yeah, so there's this tutorial that's been really helpful. I kind of picked which ones I wanted to do. You can see that they have frame buffer and then they have Bluetooth as well. So Bluetooth would be cool. It's done by a separate chip. So maybe that would be something that we'd be able to do too. The other thing that would be really interesting is on the Pi 400. If we could do USB host, we could use the keyboard and you'd get like a self-contained Commodore 64 era style CircuitPython experience, which I think would be kind of wild as well. So I think bringing CircuitPython to your TV is like really interesting, and I'm really interested in it. So obviously. Okay, so this is some USB stuff. So boochow actually did a MicroPython port. Very much similar to what I was just talking about, where it has USB host. Only if it looks like a C64. I mean, it looks like an updated C64. Good night, Felix. Yeah, we'll there will be a recording, and check the notes at the bottom for time codes and stuff. That way you can skip around. Can you use a VM and run Raspbian and CircuitPython? Folknology, that's a great idea. That was one of the things I was thinking about doing on the stream, is using QEMU to figure out what's going wrong, because it wasn't working. Let's see, what else do I have up here? So these are firmware files. So some of these files you need on the SD card. So basically what you do is you come up with this kernel image file is what you compile. And then that gets loaded by the GPU and then run on the ARM. Since the GPU starts up the CPU cores and all, could you have 4 instances of CircuitPython across the 4 cores run independent of each other? You could, but they would have to know which core they were on so that they wouldn't clobber each other. And then I don't know what that means for USB, right? Because there's only one USB peripheral still. But yeah, potentially. CircuitPython on virtualized hardware. Well, that's going a new direction. Well, Urish is actually like working on that. There's somebody in our community who wrote their own RP2040 simulator in JavaScript, and they have CircuitPython booting it in the browser on it. So here's the peripherals datasheet for the 2711. Here is the USB source code for Linux as a reference. I just got JTAG working, which I'm very excited about, although it's like half working. Here's this is the device tree that tells you like address ranges and stuff, for different things. So I'll take a look at that. That's like, if once we get to the point where we're actually like implementing I2C, we'll need that. If there are enough PCIe lanes, maybe each core could be given a USB controller on a PCIe lane. I think it only has 1 or 2 PCIe lanes. Yeah, I hadn't thought about, like, doing USB over PCIe is a whole nother thing. Okay, so this is kind of like the state of my brain. Oh, this is the other thing I've been referencing. There's this Raspberry Pi OS repo, and they have this lesson about interrupts. So they talk more about interrupt stuff. So what I was doing is trying to get, so interrupts are different than Cortex-M, because in this land, in Cortex-A land, it's designed for operating systems. And so it has privilege levels. And when something happens, it raises what it calls an exception. and that gets handled like by a higher privilege level. So there's like this whole mechanic of exceptions, and then interrupts are like some subset of that. We can see here that like there's this synchronous exception, IRQ request, fast IRQ, and then the system error that can all happen. So, and then what you do is if you get this IRQ exception, then what you do is you read from the interrupt controller which one it actually was, and then delegate. So I was working on that. That may be one of the things I have to do, but I actually had to do like a little bit earlier work of just getting the uart running. So let me show you what I've got. So I've cribbed what you see here a lot from those two tutorials, the PiOS one and then the bare metal Raspberry Pi 4 one as well. So this is not all my code. This is code. They're liberally licensed, so I've been copying it. So this is the code that starts. So when that kernel.image is loaded, it's loaded at a particular address, and it just jumps to it. So this is the first thing that you'll do. And here it's doing a check to make sure. So I think it must run this code on all 4 cores. So we make sure that if we're not core 0, then we just wait infinitely. This sets the stack pointer, and it loads us at 80,000 hex. So the stack actually lives lower than us, which is fine for now. This is me trying to set the vector table address. There's a similar thing in Cortex M0, but I think there might be multiple of these, so I'm having some issues there. This sets all the BSS section to 0, which is all of the variables that start at 0. And then it jumps to main. And in case we return, then it loops indefinitely. So that is kind of like, this is all assembly. And then this is me trying to do the interrupt stuff, which I'm not sure is working yet, but it compiles, so that's okay. We'll look at that later. And then most of this is in TinyUSB. There's 2 spots, 3 spots, 2 spots that we have to look at. So what I'm trying to do is this CDC mass storage example, and you can see the build artifacts end up here. But the things that I'm actually changing are in the board support package for the CM4. So family.c has most of the stuff, family.make, and then there's a MCU support stuff. So that's where the boot startup assembly is, interrupt stuff and IO stuff, and the linker script. So that's kind of like all the stuff that I'm changing. And this is in TinyUSB. This is not in CircuitPython. This is all, I'm trying to like get all the TinyUSB stuff going before we have, like, Timon and I have a branch that's starting to get CircuitPython running on there. But this has been a really good lesson in, with TinyUSB, because you're shrinking down the amount of code you're doing, it's easier to manage. And so I spent a couple days this week just trying to get it all building. My gut is always to use Clang, but it turned out that Clang needed libraries anyway from GCC, and it was calling out to GCC, so I finally just switched it all to GCC, and that went much better. So yeah. Simon says you could run CircuitPython on 3 of the cores and then have the 4th core for a management and user interface core, and the USB run on that, and then you can jump between CircuitPython instances via there. Pierre says looking at assembler is like looking at grains of sand in a brick that's part of a wall. Yeah. It's pretty short, which is nice. One thing it doesn't have to do is loading all of the read-only data, because it's everything's already been loaded into RAM. That's something the GPU does for us, I think. Okay, so the main thing here is, so the USB peripheral itself in the Raspberry Pi is a peripheral that is licensed from what is it? Licensed from Synopsys. That's what it is. So in source portable Broadcom, I just copied a Synopsys directory, and that's straight out of ST. So ST uses the same USB peripheral in ST devices that Broadcom uses in these Cortex-A class stuff, which is great. So most of the difficulty of this will hopefully be finding the quirks and like getting everything running. It hopefully won't have to do with like actually interfacing with the peripheral, because it'll be ideally pretty much the same. But I haven't gotten that far. So the two things I've been trying to figure out first is just blinking an LED and getting the UART output, because the UART output was not being very reliable for me. So in family.c here, this is in board-init, and board-init is like one of the very first thing that is called by once TinyUSB's main for the example gets run. So here you can see this is me blinking an LED. So these no ops here are waits. So that's just like making time go by, and then setting true and false for 42 is the pin that the LED's on, and 18 is one of the pins that I had the CLEA on. And then I have it doing UART prints, and those weren't working, and it took me a long time to figure out why, which is why I was getting to the debugger. Yeah, it's funny. You say blinking an LED is square one, but I thought it was hilarious that this Raspberry Pi 4 OS Dev tutorial doesn't actually blink an LED. It goes straight to UART. So I had to kind of like figure it out on my own. And like none of the documentation is really good for like what pin number is that on. Like I had to dig into the device tree stuff from the kernel. It's a huge gripe of mine that a lot of these Cortex-A class chips are not very well documented, because what the creators of those chips do is they just add Linux support and they call that good, right? This is the class where it's like Linux is the de facto thing that you run on it, and therefore all the documentation is really not that great, which just frustrates me to no end. So I have this example. It's got hello to GDB, and the next step I wanted to do is just rebuild it, reload it from the start, and see if it works. I got it reloading somewhat over GDB. Like this is GDB here, and I'm using OpenOCD to connect to it. But yeah, let's shut that down. I wanted to give it a shot. I found this, I was doing something really stupid. So what I was doing before, and so here when I was saying const char star greeting, blah, 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 I actually had it in the form const char greeting and then array. But this is a problem because this returns the pointer not exactly the same type. So I was having crashes due to that, and I think I finally figured out my problem, which is I needed to do this. So I want to kind of start from square one and build the example. So it compiled family.o and it linked it together, and now I have another kernel image. So the SD card is in, I'm in the right directory. So I'm going to copy that over. And I'm having KDE is crashing if I eject it, so I've been doing it that way. So now I'm putting it microD SD card in and turning it back on. And it takes about, I was surprised by this, it takes about 7 seconds for the GPU to boot. All right, so it still didn't work. I saw the blink and then it stopped working. So something is still funny. Yeah, 30 kilobyte. Was the array also on the stack? Yeah, like the address was on the stack. It was not right. Okay, so now it's not working, unfortunately. It stopped blinking, but we never got any UART output. So it definitely got somewhere down here. Yeah, 7 seconds. That's a lifetime at this level. It's not running from the card. So what happens is that the GPU copies the kernel image into memory. So this is non-interrupt UART output. Correct. So it should just pull that there's space in the UART before it writes. Okay, but it didn't work. So, and we just loaded it. So let's actually do the jlink. And then here we need to reconnect to OpenOCD. Load and backtrace. Oh, I think it reset us. So I've been doing a break at what? Actually, I think I have it. Breakpoints. Yeah, so here we can do like info registers, and this will give us the registers of core 0, which is awesome. So we have a breakpoint at board init. So, and we're at the program counter here is at start. So this is where it loads us in. So we're going to run it. We break at board init, and here you can see it's printing out information about the other 3 cores. You can see that they're just halted, which is fine. So here we are in board init, and we can do info locals, and we can see that the greeting here is correct. So let's just continue, and it didn't blink or anything. And now we're at this address 200, and there's like garbage in the stack. So this is, if somebody out there has worked with Cortex A's and has seen this, let me know. So my working theory is that something is happening, obviously. And I was thinking that maybe it was trying to, so there's different levels of execution. That's, I think EL might be execution level. Any watchdog timer is going off, maybe. Yeah, so I think right now it's not set up so that all exceptions get caught by my code. So there's 3 levels. There's 1, 2, 3, and I think there might be a level 0 as well. So what I was just starting to look into is like, yeah, okay. So there's these exception vectors. So this is for a single thing. Oh, Foamy Guy's pointing out that you can use Blinka display IO to output to HDMI. Yeah, populate all the other exception vectors. Yeah, that's what I'm thinking. Like there's this vector table base address. Show invalid entry message. Like vbar el1, I think is set. Let's see what this does. But I wonder if there's like other vbars that we have to, other system registers. Here we go. Exception vectors. The exception vector exists in a vector table at the exception level the exception is taken to. Each exception level has an associated vector base address register. Right, so that's the vbar thing. We're only setting one of them. Yeah, Rufus, it is funny that array and pointer made a difference. It's a subtlety, and like that's a common mistake I make with pointers. It's just like you have one too many or one too few. So this offset here, this 200 seems awfully suspect. I wonder if somewhere in here there's... So what if we just set all the vbars to the same thing? Reset vector address. Like, is there vbar el? I guess we could just see what the compiler thinks. The compiler knows. Where was that? In boot S. One, two, 1, 2. And then Linux after it has an ISB. Which is a instruction boundary. See, I'm not confident that if I set this now, well, let's see if it compiles. I think I might want to like restart the device. Unknown or missing system register name. Okay, so 0 doesn't exist. But I think there might be a 3. So we should be able to handle them all. And what we would do is we would just end up in, okay, so that built. Let's just do it the full way to make sure that we're in a known state. I'm not sure how much of the CPU resets when we just do a mon reset, so. This is one of the things I knew would be, this is probably one of the hardest parts I expect for getting Cortex A's going. It's just like figuring out how interrupts work. And there's 2 different interrupt controllers on the different Raspberry Pis. There's like a classic one, and then there's a standard ARM one. Which actually, and these exceptions will vary with the CPU as well. So, yeah. Okay, so I'm going to watch this. And I'll stop this OCD because it's going to be mad. So I'm going to wait for the blink. And we can actually see if it outputs anything. Or it's done. I don't know where it is. This is so much fun. Okay, so let's start ext. Ah, we're still there. Nice. Well, I don't know if that worked. Vin is It's finally cold here. She's like, you're taking my favorite bed, you jerk. Okay, she's left again. I don't know. How do I print system registers? Not sure I can. See, so the stack pointer's there, the program pointer's there, but if we do a mon reset, the program counter doesn't always change. Which I think might be, maybe we're in an exception state already. How do other working demos in Linux initialize the registers? So the working demos don't do interrupts at all, and they seem to work. So I don't know. What I did find is if I do jump start. Oh, I still hit the breakpoint. Huh. That's gotta be an exception handler. And it might be... All right, let's read more up on this. There's gotta be a way to read this state. Okay, exception classes and the ESR EL syndrome registers. If the exception is a synchronous exception, which I wouldn't expect, or an S error interrupt, information characterizing the reason for the exception is saved to the ESR EL. At the exception level, the exception is taken to. The information saved is determined at the time the exception is taken and is not changed as a result of the explicit synchronization that takes place at the start of taking the exception. The additional use cases as well. Yeah, I mean, mainly for me, it's just HDMI. Like, I've looked and looked and looked for ways to do HDMI that are low cost, and like, it's really hard to ignore the Raspberry Pis for that. Okay, so ESR, ELX, those are, we have those in, if we do info registers, we see that we have ESR, EL0, ESR, EL2. So 1 and 2 are empty, but, or yeah, 1 and 3 are empty, 1 and 2 has something in it. So it's got, let's see, 4, and then 200. So let's see if that makes any sense compared to what we're reading. I don't think so. What bit is that 2 in? ISS. Indicates the cause of the exception. Listing the valid EC field values. Okay, so the ESR EL2 has, let's see, this would be, yeah, like 36 bits. ESR EL2 is made unknown as a result of an exception returned from EL2. Like zeros is unknown reason, and that's probably what it is. Let's see, 24 bits. Each hex character is 4. Oh, so we do have a 2 in that next field. Not here, but EC, I guess, would be 1 then. Huh. Trapped WF instruction execution. Does that make sense? Maybe. ISS encoding. Like this, the ISS encoding, the ISS is blank. I don't know. I don't know what this is. That 2 would be the 26th bit. I'm like gonna be toast after this. But I can't find a lot of good resources for this, so hopefully this video will have... Does the I/O have different trust zones that need setting up? I mean, maybe, but like the other examples I've seen for UART do not. The 25th bit. What is that? What is that bit that I skipped over? IL. IL is what? Instruction length. On a warm reset, this field resets to an architecturally unknown value. PC alignment fault exception, stack pointer alignment fault exception. Any debug exception except for breakpoint. There is a breakpoint instruction. I mean, that seems plausible to me that it's an alignment thing. I don't know. What else do we have here? Like, this looks like junk. But maybe it's not. ELR, EL. SPSR, I think, is stack pointer for the particular level. Let's just see if we can see what ELR. ELR. What was it? Is that what it was? ELR, EL. Not found. ELR, EL. To run code at non-secure. Hey, Set. Could you instruction trace in GDB until it crashes? Yeah, we could try. I'm really, like, for some reason, like, reset doesn't work. But, like, the program counter is still 200. Which I don't understand why reset doesn't work. Like the stack pointer is where we want it, but not the program counter. But if we do jump, it still does it. It could be like a bad address. What happens? Like, I've gotten output from this though. That's what throws me off, is like, I don't think I'm doing anything weird that I haven't done before. I mean, maybe it's an interrupt. Maybe we should try to read the interrupt register. Like, if it was an interrupt that we weren't servicing, then we would definitely have a problem. Let's try to read this. I appreciate the pain during debugging and trying to figure out how to make progress anyway. Well, that's what this is all about. Okay, so there's nothing pending at that register, which is some magic address I pulled from somewhere. I mean, there might be... Like, I don't think there's like an SVD file. Is it B? So it doesn't look like there's anything there. Yeah, it feels like a instruction alignment problems to me. The other approach I was taking was and maybe this is worth doing too, is the reason I have the Salier out is I can have the code set pins high and low as it progresses. So with that, this is what I was doing before the debugger, so that you could see like the sequence of things starting up, which might be worth doing to figure out where it's stopping. Print to a pin debugging, yeah. The nice thing about using pins like that is that it means that your code can keep running, which should not be underrated. Same with printing. It would be nice if we were printing, but that might be our problem. What did I change? I don't know. Let's see if we can get the GDB2 grading out, which is commenting that out. I feel like this print call has caused me a lot of headaches, even though I thought I fixed here as well. So let's just give that a shot. And let's make this a while true. So we'll just hang out in this loop. Faster than printf to serial. Yeah, 100%. Pins will be faster. Okay, so I'm gonna rebuild, and this time, and again, I'm gonna just do it with without the debugger. I just don't trust the state that the CPU, that the debugger gets the CPU back in, which is why I'm like starting fresh, which is a pain, but this will bring up stuff. Okay. Plug it in. Power it on. I'm looking for the blink that happens before the print. Nope. Nothing. What the heck? I mean, maybe we're faulting sooner now. That could be entirely possible. Like, I wonder, like, we added these things. If we go back to just the one. This is all like, I mean, I'm learning like a new class of CPU, so you can't expect it to go perfectly smoothly. Ooh, yeah. What does the logic analyzer show on pins? It's not hooked up right now. I will hook it up shortly. I am curious how Circle initializes everything. Overwrite. Safely remove. Let everything crash and come back. Because, you know, that's good. Alright, look for the blank. Yeah, I should do the... There's the blank. And there's the hello. Okay. There's a startup 64. Let's take a look at it. In boot. Armstub. There's a start. Read write cache latency. Floating point SymB. EL3 vbar. Setup GIC. So that's GIC is the interrupt controller. switch to EL2. Boot kernel. Whoo boy. Startup 64 in live. Okay. Chain boot works. Oh, it's from U-boot. Enable EL1 access to timers. Coprocessor traps. Init exception vector table. I didn't realize there were so many bare metal RPi projects out there. Not enough. Start secondary. Okay, that's for the second core. Check if we're in EL1T mode. I don't want to actually take anything from GPL stuff though. I mean, it could be an exception level thing. It would be nice just to figure out how to figure out where the heck I am. Let me just cross my fingers and hope. I did have to add these knobs into here. .42 is the LED. Build again. I wonder if the 200 is just like from the debugger. But I've definitely had it before where it wasn't. I uncommented something and it's smaller by 80 bytes. Like, how does that make sense? I should set the CLU back up. The LED is off. We did not get a second hello to GDB2. Like, where are we? Where? Oh, maybe this stopped us? Ooh, we're importing it. Next. Yeah, see, that's the problem, is I can't really... Well, I mean, that's where... What is my stack pointer when I'm trying to do the stack trace? The stack pointer is what I would expect. It's 7FFD0. So what is... How is the stack initialized in the way the debugger expects? That should be the compiler. Like, the compiler should be doing all the proper stack stuff. When boardinate or when main is called, right? So we should see a main boardinate something else. 32T. Let's just do 0x7FFD0. I mean, I guess these should be... DF0. Should these be 64 bits? No uint 64. That's weird. That's okay. I just wanted to print this out. See, like, what's D? And then 4, 8. B. Info stack. See, so this is kind of weird. Like, the backtrace is getting it from somewhere else. Doesn't GDB have a way to hex dump memory? Yes, I'm sure it does. Does that mean I remember how to do it? No, it does not. Like, where is it reading? Well, this is interesting. That this ESR EL2 is pretty full. Like, there's a bunch of bits set there. SPSR. I don't know if we're ever... I don't know. I am out of my depth. If EL equals 0 and CPSR, were you at EL2? I don't know. I thought about that. Like, the program counter is here, but the stack pointer is still kind of where I would expect it. But why is backtrace then giving me garbage? It doesn't actually look like... D0... E0. 855, 5 done 3. I think this is out of the range of hardware watch point on the execution of 200. I've already got a breakpoint there, and that's what I just hit. Like, we're on this breakpoint for, like, that. I think that's what you mean, like a break. Watch point on execution is a breakpoint. So let's just see, arch64 gdb level. ARM, what is the current execution mode? This is handy. Depends on the execution mode. Current EL. Once an exception comes, can I read any register to determine whether I'm in S error, synchronous, IRQ, FIQ, exception handler? If I'm in EL0 mode, reading CPSR causes an exception. I don't think I should be. Like, that's the other thing. We could try running this in QEMU. That might give us more information. Let's try that. I want to play around with that. Let's see what QEMU says. I've never done this before. Let's do it in a different. Let's do it in here. QEMU. A lot of this is things I haven't done before. Let's find the... So there isn't a board definition for the Pi 4, but the Pi 3 is pretty similar. Raspberry Pi. Oh, that's what I wanted. Right here. Oh, I'm in the root, so it would be examples, device, CDC, MSC, build, Raspberry Pi, kernel 8. My like CPU, my actual CPU like kicked on. It's like, oh, I gotta emulate something. Okay, so that's a start. We don't need the graphical output. Is there a virtual jlink for QEMU? Yes, there is. You can have QEMU do a GDB server. I was looking at that. Dash no graphic. Thank you, Mark. Does it emulate ARM74L Arch? Yes, I think so. I think you can do all the way. Yeah, I think you could do 0s through 3s, and they just haven't added the 4 stuff for QEMU. And in fact, I think you can emulate USB hosts. So I was thinking, like for debugging USB host stuff, this could be a good option. Okay, where did I see that? Here we go. This is the person that added it. This is the compilation. Here's how to run it. QEMU GDB. Okay, this is what I was thinking of. -S option makes QEMU listen on port 1, 2, 3, 4, and S makes it stop at execution until you give it the continue command. No graphic, lowercase s, capital S, like that. And then let's turn this off so we don't get confused. Let's turn this off. That's okay, we'll get rid of that. And then let's do arch. That, and I have this, I have a GDB startup that's not right. So it times out. But now we should do tar ext 1, 2, 3, 4. Okay. So now let's see what continue does. And it kicks on, so I know it's running. And Control C, and hey, we're in the same place. The stack is slightly different, but we got to 200 again. That seems good. That the emulation did the same thing. We're in line 56 of main. What is line 56 of main? Source, main. 56, Boardinate. Okay, so how do we do uart? QEMU uart. The ARM docks are quite handy sometimes. There's a lot of ARM docks. I think that's the challenge. You can add virtual USB serial ports. I don't want to telnet. Oh, booting a bare metal system. What? For ARM v7, eh? But that's close. Enable interrupts. So that's in the programmer's guide for the 7. Booting a bare metal system, boot code. I think I have the... This is the reference. But I'm sure that there's a... Perfect. Y'all are so helpful. Bare metal boot code for ARM v8 processors. In arch 64 mode. Let's see what it says. Setting up vector tables. There are vector tables at for each exception level. Can be read. You must place boot code at this address. I don't have any Blackfin experience. Oh. See, the problem is the GPU probably could actually be doing stuff before us. Like, this is what I was trying to get set up. I tried to do that with all the same thing. Only 53 pages or so, I know, right? It's got example code. EA, IRQ, and the FIQ bits. Huh. Initializing registers. System control registers. Huh. So what do the other bare metal system demos do to freeze the GPU? I don't know what you mean by freeze the GPU. Like, these other simple demos, they don't do a lot. Like, I really don't. It's probably going to be like, oh, when we get it, but... Stop the emulation. System reset. Can we like go back in time on QEMU? There's got to be a way to just have it print everything, right? Oh, I thought the GPU was interfering with our code. Yeah, maybe. Dump guest memory. Log. I mean, reverse execution. How do I reset? Is it mon reset? I mean, I don't really need reverse execution. I need like QEMU to just tell me. Reverse step. I wonder if it works. I guess I could set a breakpoint. How do I set a breakpoint on that? No. No. Hey. Let's see. Let's also break at ordinate. Try to blink an LED on a Pi. I got that far. System reset, continue. Okay. So we did boardinate, and now we continue, and now we're here. And we do reverse step. Ah. Want. Like, sorry, my instinct is to like use my full monitor. All right, we got 20 more minutes. QEMU is pretty neat. QEMU PC log. Logging and debugging for QEMU virtual machines. QEMU monitor. I mean, that's what we're getting through mon. Info. ARM EL numbering uses a convention reversed from x86 rings. Well, so I don't know either, but that's good to know for the future. Info registers. Mon info block. Ooh, there is temp QEMU log. Mem save. On help log. Remove all the logs. Show trace. What do you think TB is? Log MMU related activities. Log when the guest OS does something invalid. Ooh, got a delivery. What do you think TB stands for? On log CPU. Sure, why not? And then, ooh. Oh, you know what? Maybe we should. Ooh, that looks nice. Look, there's our P state program counter. Why is our program counter? That doesn't look right. I don't trust this. This doesn't look like it's the right. How do I turn it off? Just like that. On help CPU. Set the default CPU. On help log CPU. These don't look right. This just looks like the same thing over and over again. QEMU. Docs. Never trust so many zeros. Exactly. GDB usage. Let's take a look at that. Debugging multi-core machines. Separate inferior. Info thread. Well, that makes more sense. That the program counter of the other 3 CPUs is what we're printing out. How do we log the CPU we care about? Log CPU 0. Log CPU 0. Show trace before log none. Exec. This is pretty neat. I'll give it that. Trace. That doesn't look nearly as helpful. Well, that looks like program counters. Of everything else. '81, '84, '81, '88. That's it. 81, 88. Like, I don't care that there's 4. I don't care that there's 4. Use a Unix socket, which I don't care about. Single step behavior. Memory mode. I don't get it. Why can't you just tell me what's going on? invocation. Debug/expert options. Serial. Parallel port. Run the emulation in single step mode. Use -d help for a list of log items. It so bothers me that like the same thing happens. Translations blocks. $351. Trace. Compile with simple log or ftrace tracing backends. Trace is what I want. On log. On help log. On log. Done. Mon help. Trace event. What is single step mode? Oh, maybe this is the trace output. Can I not Control C it? Oh. How do I stop it? Oh, come on. Rabbit holes after rabbit holes. It's very reassuring to me to see you struggle as much as I do sometimes. You're welcome. Come on, help. How do I quit? Control C doesn't work. System power down. Control Alt Delete. Oh, that's not what I want. I'm trying to quit QEMU. Oh, there's stop. Stop capture. Like, if I can't control C that. Can't find process. Oh. Cool. There we go. Control AX. All right. Thank you. It did work. What is this trace stuff? Tracing pattern. Why doesn't Control C work? Trace help. QEMU. Help. This list really long. GIC is cool. Oh man, I'm gonna like this once I figure out how to use it. This list is like not sorted either. And this is like everything. CPU in, CPU out. QEMU trace arm. How to use the simple trace backend. Oh, Control C is supposed to be sent to the emulated machine? Yeah, it reminds me of screen. Tracing and profiling. Ooh. Let's try that. Control C's copy. DNASM. Okay. And what is the configure, like no configuration file thing? NH. There we go. Well, that's pretty straightforward. I still see Alt-Tab as scroll up. So we're returning from where? I mean, that's super cool. I guess we could look at the map. There's got to be a version that's... Disassemble board init. Oh, you know... Board uart. CE. What is it? It's an 81. Like, the stack is wrong. 81C. CB, CC, CD, CE. I guess that's GPIO call. GPIO issue. What more can we trace? Tracing QEMU guest execution. It's still not that useful. Like, it must be... Like, if we did the return... Then we return to the wrong place? Or this is just... Is in ASM just printing everything out? Oh, I'm over time. Or is that just telling you the stack is hosed? I don't know. It seems like what I keep expecting to find is just to like run it with these settings and you'll be able to see like all the I guess I kind of want register state or like exception level changes. In ASM. Like that's definitely on the right track. Oh. If you're lucky, then one of the sample plugins might even be sufficient for your purposes. The CPU and the exec traces, which is what we looked at. Sounds like in ASM is not actually what we want. I wonder if there's a way to hook Python in. Example plugins. Hot blocks, hot pages. I'm almost done, I swear. Oh. Like, what is this? Like, I don't see a 200. This is just trace again, isn't it? Can I only monitor one thing? Log one thing at a time? It's got to be in here. It's just we're looking at all of the cores. Sorry, folks. I know this might be boring. Python hooks in GDB, that's true. I just want to log one CPU. I really hate it when people come to me and say, I just. It drives me nuts. Like, it looks like this information would be helpful. It's just not the right cores. It's like all the other cores. Cool. Let's wrap it up. Thank you all. I know I'm over time and you all are headed out too. I just want to go to the moon. Exactly. Okay. This has been another deep dive with Scott. Thank you all for hanging out and hanging in there with me as I explore Cortex-A and QEMU and all of that stuff. Pretty interesting. Hopefully, like, it makes me very happy that QEMU can replicate it as well. That means that I don't have to use the Raspberry Pi to figure it out. So that's exciting. Check out next week. We'll be at 2 p.m. Pacific next Friday. The week after that, we will not be doing it. Thanks to David for taking time codes. Thanks for Patrick for getting everything in the notes repo. If you want to support me and support Adafruit, go to adafruit.com, purchase some hardware there. I'm playing around with the CM4 IO modules and boards, and I think we do have some of those in stock. So you could play around with that if you like. And if you want to join us on the Discord and talk about all time, you can go to adafru.it/discord. And Jeff's asking off topic, but does the STM32 767 CircuitPython support work? If the board's on there, we thought it would work, but not a lot of people are using it, so it may have failed. Jeff, I would suggest joining the Discord, and we can ask and chat there. Go to adafru.it/discord to do that, and I'll put it in the chat as well. Thank you all again, and we'll see you next week. I will pet the cat since he's here.
Spook. Thank you, kitty. You curled up.
All right, have a great weekend, everyone.